about 15 million copies sold. His daughters have pretty much made a living by revising it and re-releasing it. 1981 was the latest. I received this from Christopher Hancock. Mr. Hancock apparently believes I need to polish my people skills, and he may be right. He is a radiologist out in Palm Springs. Kind of a background in genetics, and does a lot of spine work, neuro radiology. Most interestingly, in recent years, he's kind of pioneered the sharing of radiology imaging on the cloud out in Palm Springs, California. Thank you for the book. I also heard from Rich Morris up in Madison, Wisconsin. I had told you all about his 1962 Studebaker pickup truck up in Minnesota. Unfortunately, he lives in Wisconsin, outside of Madison. He and his wife have built their own home out in the woods. He has an engineering firm there that they're going to restore the 1960 model Studebaker. He was down, picked up his UQM Power Phase 100 and a bunch of batteries, and I have now sent him his two Lear chargers and a DC to DC converter with controller. While he was down here, we went to a wine dinner, and so he has sent me a couple of bottles of Pinot Noir 2012 from Wallersham Winery. Kind of interesting. Thank you, Rich. The Wallersham Winery is in Prairie du Sac, Wisconsin. But what's interesting about it is they, I don't believe they've been in continuous operation, but it was originally planted as a wine property with vines in 1840, making it one of the oldest wineries in the country, in one sense. And nearer to my heart, they are opening a distillery this coming August. And so they'll be making a little whiskey, probably a brandy, actually. Anyway, thank you, and we continue to follow Mr. Morris's work with the Studebaker. I think it's going to be a very interesting vehicle with certainly some nice components in it. Oh, what else do we have? This week, a Chinese automaker, Aoxin New Energy, has announced a car, the Aoxin Ibis. It's aluminum and carbon fiber. It's a little longer than the Model S, but weighs less at 4,034 pounds, 181 horsepower, and 285 miles per charge. Upscale interior. A lot of the Chinese sedans, they like to have a driver and the owner actually ride in the back. And so Tesla's even looked at doing a stretch version. And that's kind of interesting. Tesla, meanwhile, has struggled in China. The latest is a hoot. Sunday in the Tangzhou Wanda Plaza Mall in the Tangzhou district of the far eastern suburbs of Beijing. Tesla hired a booth and had two Model S's there. A 5-year-old boy got in one, got it started, and drove it away, striking a stroller and knocking a baby out into the mall floor. Neither child was hurt, but it caused quite a stir there at the mall with the Model S. And so that's kind of interesting. I did talk last week about responding to the wannabe price war with EV West over the HPVS motors. That's going pretty well. We're not making any money, but we're selling a lot of HPVS motors. But I thought it'd be a good time to note that they have a new model. I don't have it up on the website yet. I'll try to get it up. This goes back to Anna and the boats. Brian Seymour is actually kind of a boating enthusiast and did not think electric motors would be appropriate for boating use. And after watching Anna's, he built one himself. There's a little difference in the way you use a motor in a boat and a car and an airplane. In a car, it's stop and go, and you apply power, and then you roll, and so forth. And so it's very intermittent use. Boats and aircraft tend to run the motor at a continuous rate, and typically at one of high power. And that, of course, causes cooling problems. So what he has done is developed a very interesting variant of the AC35 times 2 and the regular AC35 for marine use. And that includes some gland nuts and so forth on the cables to make them waterproof. Putting it in kind of a stainless and aluminum can and bathing the motor in mineral oil. There are some non-conductive mineral oils that can be used for cooling, and basically he's built a liquid-cooled motor that actually the rotor and stator and so forth are entirely bathed in mineral oil. And you circulate mineral oil through there, and then you have to route it to a heat exchanger. Well, on a boat, you can do some interesting things with some through-hull heat exchangers to where they're actually exposed to water outside the boat and get some remarkably effective cooling. And so this is the AC series from HPVS really hasn't had much heat problems in a car, despite the fact that it's our only AC system that's not liquid cooled. Now, we do liquid cool the Curtis, and one of the problems I'm having with our price war with EV West is that we always include the chill plate. And so that's right now, I guess I'm paying people the chill plate to take the motors from us rather than EV West. In any event, their stainless version, this is their first liquid-cooled motor, and a very creatively liquid-cooled one. Now, they're kind of, not a stock item. It'll take a few weeks to. In fact, we've got HPVS back up now where it's a couple of weeks to get a motor, which is not a bad, it's 10 days or 2 weeks. It's not a bad lead time. The steel version is, of the 35X2 is $1,000 more, but has very effective liquid cooling. And that's so you can run it at continuous power in a boat and get rid of the heat. And recall, electric motors are almost entirely about getting rid of the heat. That's the only issue on power. There's no limit on power on an electric motor in some sense, other than just getting rid of the heat. And so this is a very interesting take on that. The things just keep getting worse in the electric vehicle world. They're kind of taking a hit on the gasoline. I reported last week. This week we have recalls. GM, this is comical. GM has recalled 64,000 2011 to 2013 volts. Apparently, this does not apply to the 2014 volts, and I don't understand why. But the recall is over carbon monoxide poisoning. Apparently, GM has devised the only electric car that you can have that is still good for suicide in the garage with bicarbonate monoxide. what happens is, if you go off and leave the car on, and this actually is kind of a danger of electric cars. I've done it myself numerous times, because they don't make any noise or any fumes. You pull into the garage and get out of the car and forget to turn the key off and leave the car on. And the Volt has a peculiar element in that when the battery charge gets down to a certain level, it turns on an internal combustion engine to recharge it. So what they've had, and there's actually been a couple of injuries apparently, no deaths I don't think, but people come in, park the car in electric mode and forget to turn the key off. And it sits there and discharges the battery until it reaches the point where the battery is sufficiently depleted. The internal combustion engine kicks on automatically and then fills the garage with carbon monoxide rather thoroughly in an enclosed space. And the owner or driver returns later to come into the garage and finds it completely filled with carbon monoxide. Problem with carbon monoxide is it's odorless and tasteless, and if the car ran out of gas then and sat there, you can have a room full of carbon monoxide and not realize you're in it. And it's made several people sick, apparently. So they're recalling 50,249 Chevy Volts from 2011 to 2013 model years in the U.S., and an additional 13,937 exported. That's you, John, with your Ampera. Get your software upgrade so you can avoid this problem. There is a interesting thing. There's a dealership out in California. If you happen to be looking for a killer deal on a 2015 Chevy Volt, want to use it to end your life, perhaps, there's a dealership in Northridge, California, called Rydell, and they claim to be the largest seller of Volts in the country. And you kind of see why. This is a California outfit. They will lease these cars to anyone, anywhere in the country. Right now, they're running a $149 per month, 36-month lease on the Chevy Volt. That's with $3,550 at signing. Or $248 per month with nothing down at signing, and that works out pretty much dollar for dollar. There's a penalty of 25 cents per mile for anything over 10,000 miles a year. If you assume a similar car would have a 25 mile per gallon thing, that's about 400 gallons per year. At even today's $3 per gallon, that's about $100 per month. And so technically you could put $35.50 down and drive this car for $49 a month for 36 months. They're in Los Angeles. The website is www.chevynorthridge.com. And speaking of recalls, Toyota is now recalling all 2,500 of the RAV4s that Tesla made for them. Apparently there's some sort of software problem. You'll be driving down the road, and it will auto-magically shift into neutral, leaving you with no motive power at all. And so all 2,500 have been recalled. There have been no crashes or injuries that we know of, and we know of several people that have that Tesla-powered RAV4 and love it. Apparently being in neutral isn't too big a deal. The New Jersey State Senate Commerce Committee has voted to allow Tesla sales in the state, despite their dealership things. Recall they had a big deal over that. Now that still has to go to the governor, and who knows what he'll do. He's currently trying to get a presidential campaign off the ground and is about to emoliate himself with gasoline, by the way. New Jersey and Exxon Corporation has had a running lawsuit starting from the premise of Exxon admitting that they have absolutely butchered a large piece of real estate with a refinery that can hardly ever be cleaned up. And they are paying to clean it up and working at cleaning it up. But in addition, the state of New Jersey has sought damages and has a lawsuit that was running, it's been going on for 11 years. Just in the past few weeks, the state attorney general and the judge was just about to rule on the case. And rather than let it go to the ruling, the state attorney general, at the behest of Christie's office directly, has asked the judge not to rule yet because they're going to do a settlement, and the settlement turned out to be for $225 million. And this is a curious low amount for a $9 billion lawsuit, which is what they were seeking, that was just about to be ruled on. And Chris Christie apparently has got something going with that. I think it'll be the end of his political career. So who knows what he'll do about Tesla in the thing. Formula E today is having their first U.S. race, and but they have spent $100 million, according to the organizer, to get this thing off the ground. It has developed a bit of a following, but this week the Discovery Communications, the owner of Discovery Channel, and Liberty Global, another cable programmer, have taken a minority interest in the property Formula E. So that they should get better exposure that way, instead of just YouTube, perhaps on the Discovery Channel, and we think it gives it legs. Let's see, what else do we have here? Yes, Tesla's the car of choice for 5-year-old Chinese in malls everywhere. New device just in and already a collectible. If you'll recall, a few weeks ago I ran a little video by a guy named David Seabury, who had a great idea, and that was to create a Arduino-based CAN-driven driver for legacy instrument clusters. It takes CAN messages off the CAN bus and then converts that to PWM outputs to run LEDs and lights and gauges on your old-style instrument cluster that's not CAN-driven. And I know a number of people that need this, potentially including me, so I'm going to keep one. He inquired as to what I thought of the product possibilities with this, and I responded by telling him, hey, what do you want for him? And he told me, and I said, well, hey, give me 10. If we sell those, we'll order 20. And that's how it goes around here. And so off and running we were. What David discovered, I have known for some time and have kind of been drug kicking and screaming into this development of electronics products because it's so icky. And it's not icky, it's a lot of fun to design the hardware and the software for it and get it to work. That's not any of the work. It's the putting it in an enclosure, the wiring, the piece parts and peripherals. And David, on delivery of his 10 units, announced to me that there would never be an 11th. He was done. Having built 10 of them, he's finished. He doesn't like this assembly work any more than I do. And so we have an instant collectible. I'm keeping one. The other 9 will be up for sale on the web store. If you think you have a legacy instrument cluster and are going to be dealing with JevQ and CAN bus for your AC drive system, this is kind of a neat little device. I think we're going to put it up. Since it's a collectible, kind of high, it actually cost me quite a bit too, but we'll say $295, and we'll put those up. And that takes me to a little bit of talk. We have talked about our JLD505. This derives from a couple of things. The JevQ can get battery information, battery current voltage from the inverters typically, but it's pretty rough, and we don't really have good data on the battery for our JevQ system. This is a prototype of the JLD505. At the same time, I have people that come to me quite regularly and say, Jack, you know what? I believe you. I have watched your show. I see how you deal with the batteries, and I agree that the battery management systems are a poor choice. And I've been living BMS free for yay many days. However, and then some story about an insurance company or a show organizer or some sort of competition with a university that require a BMS. Now, what's interesting about this is that they don't really define what a BMS is in most cases, and they don't entirely know what a BMS is in most cases, but they're going to require one for the safety of all the participants and to prevent fires. Battery management systems have been the source of most vehicle fires in the electric car community. So the irony is doubled. However, it occurred to me that we can simply design a device that's what I like to refer to as non-incendiary. In other words, it does not cause a fire. And if we label it a BMS, and you bought it and installed it on your car, I guess you have a BMS. And if anybody asks if you have a BMS, the answer would be, sure, I've got one right here. If your insurance company wants to know if you have a BMS, see, they never did settle on whether BMS even stood for battery management system or battery monitoring system. So there is no definition of what a BMS is anywhere that I know of. But yet people are requiring them, and people want to have them because other people have told them they need them, mostly people that don't know anything about lithium batteries. So very ironic. It appeals to my sense of whimsy strongly. And so Paulo and I have just had a ball with this. We used to have a product that does count coulombs and voltage and lets you keep track enough of your battery that you would want to driving the car. And it's called the JLD404, so we call this JLD505. And after months of delay, I've finally gotten a set of the initial 20 boards for test from China, if they actually operate well. To get another 100 is sort of an email, do it again, Sam. And so that's where we're at on this. And they are in DHL's possession, but not in mine. And there's a lot of software to be done to make this real. And so it will not be appearing on the website imminently. But it's going to be an interesting device. And let me, and it is about current measurement, which we addressed last week. So let's take a look at what I'm doing in the back in the shop. Again, not terribly automotive. We're not driving down the road, but in the winter here, it's we're not missing anything. And see about the JLD505. Last week, if you recall, we talked some about current measurement and the CAB 300 can-based Hall effect device for measuring current with isolation and reporting the current via can. And I like that. However well you make a Hall effect device, it probably can't ever approach a shunt-based current measuring device. And until recent years, all laboratory and scientific work in the measurement of current was done with shunt resistors. They have a new technique now, but it's a little bit of a setup. Let's don't talk about that. Let's talk about shunt resistors. From Ohm's law, we know that George Ohm was right, and that the amount of current flow will be directly proportional to the applied voltage and inversely proportional to the resistance it encounters. And we can take that a little further and extrapolate that if we run current through a known resistance, that the voltage produced will be a function of the current. And by measuring that voltage, we can determine what the current is. To do that effectively in an electric vehicle or any high current device, you have to have a very, very low level of resistance. And in fact, you may have seen me in the battery lab, in addition to referring to our current meters, to also put a multimeter across one of the shunts and actually read the voltage to verify the level of current. What has emerged over the years is some high current shunts that use a metal called manganese. When you do pass current through a resistance, no matter how small, it does heat up the resistor. And in this case, at very low values, but that heating over time can throw off your current measurement. They have developed a metal called manganese, which is a alloy of manganese, copper, and nickel, that because the three metals expand or react differently to temperature, and their conductivity changes in different directions with regards to temperature, it kind of cancels out the thermal effect. And so most modern shunts are made from manganese and are a very small value. They tend to be rated in three ways, and two of them you're familiar with. And we're going to talk today a little bit about the third. This is an 800 amp shunt, 75 millivolts. And what that means is that the resistance of this is such that you will read 75 millivolts from one of these little terminals to the next across the shunt part at 800 amps. This one will likewise read 75 millivolts at 1,000 amps, whereas this one down here is a 300 amp 75 millivolt shunt. And this is a 500 amp 50 millivolt shunt, it'll read 50 millivolts at 500 amps. A lot of you get very wrapped around an axle about having the right size shunt for the amount of current you're going to use. It's a little more complicated than that. You do want to have a shunt big enough to handle your current. Typically, it's very safe to handle 1.5 times the stated amount of current. So this 500 amp can carry 750. This 1000 amp can carry 1500 amps. In actual practice, you can double it, and we have routinely done so, taking a 500 amp shunt and run 1000 amps through it. You get a little more heating, and so your accuracy at 1000 amps is not quite as good. On the other hand, at 1000 amps, how much accuracy do you need? And so we tend in a car to drive where we're driving at 1000 amps for 6 seconds and at 110 amps for 6 minutes. And then we're sitting there at no amps for another 6 minutes. And so it's not a continuous duty situation at all. The shunt doesn't quit. In other words, if we're doing 1000 amps here, if this is a 500 amp, a 50 millivolt shunt, then at 1000 amps, it's simply reading 100 millivolts. If your display device will go that high, it's not a problem. And so this is our JLD505, and it uses these shunts to measure current. How accurate is it? Well, it's got a pretty good circuit in it. This little JLD505 we've been selling for several years. I talked to a guy this week who put one in an RV and was absolutely astounded at all that it would do. And indeed, I told him that I thought with the 2 control relays on here, that if you gave it sufficient thought, added some external contactors, you could probably run an oil refinery off this little meter. We've just found it to be very good. Shunts can be expensive. The JLD505 is Chinese, and it assumes, like these Chinese shunts, that they're 75 millivolts. You can't change that. But you can change the size. So you can change it from 75 millivolts to 500 amps. You can change it to 775 millivolts, 1000 amps. It always stays 75 millivolts. Well, here's a 500 amp shunt, but it's 50 millivolts. Can you use that with a JLD505? Absolutely. This is real simple. If it puts out 50 millivolts at 500 amps, how many amps are we talking about for 75 millivolts? Well, 75 is 1.5 times 50. 1.5 times 500 would be 750. This is exactly the identical resistance that a 750 amp 75 millivolt shunt would be. It's just marked 550. The resistance is exactly the same. The 750 at 75 might be built a little heavier to carry more current longer. We're never in a situation where we need to carry these high currents for any length of time at all. Now again, if this is 50 millivolts and we're reading 500 amps, that is about 10 amps per millivolt. And so we have to be able to detect a 1 millivolt, 1/1000th of a volt change to discern 10 amps. And so 1 amp would be 1/10 of a millivolt, or about 100 microvolts. And so that's what we would need to do 1 amp. To do 100 milliamps, we would have to be down around 10 microvolts. And so you get into very low voltages to discern light currents. Here's a 200 amp 75 millivolt. Well, in that case, you're only reading about 3 amps per millivolt. The result is this is much more accurate because you have less current represented by more millivolts. 1,000 amps, 750 millivolts, you're talking about 15 amps per millivolt. Here we're talking about 3 amps per millivolt. And so when you go to a smaller shunt, you get more resolution, not really accuracy, resolution, granularity. Accuracy is a different matter. So our resolution gets better with the smaller current devices, and it gets poorer with our largest ones. Let's talk about accuracy. These Chinese shunts are what they call a Class 5. Class 5 means actually that it is good plus or minus 0.5%. The resistance on this shunt will be within 1/2 of 1% of what's advertised. This 50 millivolt 500 amp happens to be a Class 2.5, and that is another commonly available shunt, and that will give you 0.25 or 1/4% accuracy on your resistance. There are lower ones, and the price goes up as you go down. For our JLD505 project, I've just ordered 100 IMCO 400 amp 100 millivolt shunts, but they're Class 1, and that is 0.1% plus or minus on the resistance of the shunt, and so it's accuracy. And so by going to 100 millivolts on 400 amps, I get better resolution, about 4 amps per millivolt, which is down like this 200 amp, but with the ability at 400 amps to easily go 600, and that covers almost everything we would do with a high-performance electric vehicle system. But increasingly, we're going to higher voltages where about 400 amps is actually our peak, and we do a lot of stuff in the 100 to 200 amp range. So I kind of went back and forth between a 300 and a 400. Decided to get a 400, but doubled the price of the units by going from 0.25% to 0.1% accuracy. I could have doubled it again and kept the same accuracy, but got a NIST certificate with it. I didn't think you all would care a whole lot about having a NIST certificate. And so those are the 3 parameters on shunts. And what the current actually is, it's not a limit, it's part of a ratio. 500 amps to 50 millivolts, 400 amps to 100 millivolts, 200 amps to 75 millivolts. And to get the resistance is very easy. You divide the 50 millivolts by 500 amps, and you get 0.0001 ohms. And I may have that plus or minus a couple of zeros, but a very small amount of resistance, which is what we want, but a very accurate level of resistance. So when we measure 10 millivolts through there, we know that's going to be exactly 100 amperes. And if we go to 9.9, that's going to be 99 amperes. And that's how current measurement works. This, I thought I would show you. It's a nice device. We call it David Seabury was doing us a Arduino project to drive legacy instrument clusters, and he did a video on it. I bought 10 of them from him, and here they are. They have, let's see, a whole series of outputs. Here's your 12-volt ground to power it. This is your twisted CAN wires, and so you can enter, this thing will receive CAN and interpret them and use that to drive instrument clusters. He was all enthused about it, sent me a video of what he'd done. I was all enthused about it. He wanted to know about making it a product, and I promptly bought 10 of them from him. It's taken him a month to put them together, and he's advised me he's never going to do an 11th. Forget it. And this is what you get into with this kind of technology. Doing one is a very creative act and a lot of fun. And getting it to work is a very satisfying experience. Productizing it is something else. There's no book on this. There's no box. There's really nothing here. And so we have to add all that to make it a product. And I have 10 of them to sell, and when they're gone, there aren't any more. We're talking about some options, maybe buying his software and putting it on some of our hardware. I don't know what we'll do there, but there I have it, 10 of them. Come and get them. When they're gone, there's no guarantee there'll ever be any more done. As I said, we've sold a lot of these JLD505s. They let you see your voltage, your current, and it will accumulate ampere hours. And so you can tell how many you've taken out of your pack. It'll account for charging and regen, current back into the pack. And so you can kind of use that as a state of charge meter. It has some 0.56, a little over a ½ inch tall, bright LED characters that even my eyes can see. And so this has been a very popular seller. You know, I've had several people approach me and say, you know, I watched your show. What you were saying made sense to me. And so I, too, have been living BMS free one day at a time and have gotten good results. I've been driving my car for 10,000 miles or 12 months or whatever. And it seems to be working. However, I went to this car show in Pennsylvania, and they wouldn't let me enter my car because it didn't have a battery management system. And they said I posed a fire risk to the rest of the entrance to the show. Someone else told me, I've lost my insurance because I don't have a battery management system. They say I have to have a battery management system. Now, we can argue and break into violent agreement about what idiocy this is. The people that are requiring it don't have any detailed requirements. They don't even know what a battery management system is in any specificity. But they feel that there's a danger with fires. They're caused by battery management systems, normally, ironically. But they think the solution is a battery management system or battery monitoring system. There is no consensus on even what the term BMS as an acronym stands for. And so I thought about that and thought, well, you know, there's no harm measuring batteries. We're not going to balance them or try to set them on fire. But if we did a non-incendiary device and called it a BMS, you could install it, and if anybody wanted to know whether you had one, of course you had one, and here it is. And further, some of the basic functions that anyone knowledgeable, and normally they're not dealing with anyone, nor anyone who is knowledgeable, but in case they happen to be, a battery management system often measures voltage, current, and temperature of the battery pack. So let's take that as the mission. And I went back and forth with Ed Clausen and Paulo Alameda, and we came up with 2 projects, and so far Paulo's in the lead. And here it is. Since this is famously known as a JLD504, and we have no idea what the JLD stands for, we will call this device the JLD505, mostly because that tickles Paulo's fancy. And it's just as good a name as any other. It's the JLD5 battery monitoring system. And so we went back and forth with what that would look like. And anytime you start a new project, my approach is not to use the tried and true, but let's go find out what the latest releases are in semiconductors and see if there's anything to be had there. I recently sent Paulo some brand new Cree silicon carbide MOSFETs that now can do 1200 volts, which was always the limitation on MOSFETs, was voltage. So we took a look at this and have come up with something going back and forth as far as functionality and chips. We had a disagreement on the multi-controller. I wanted to go to the same one that's in the Dewey. Paulo didn't want to for some isolation reasons primarily, which I understand. It's just I think we're going to wind up regretting that in some ways. But right now we've got plenty of horsepower, 16 megahertz, 32K flash RAM, plenty to do what we're going to do. And we decided that we wanted it, of course, to do three things: measure current, measure pack voltage, and measure temperature. And the most important, I think, is current or Coulomb counting. By accruing those carefully over time, we can count ampere hours. By accruing current and voltage over time, we can accrue kilowatt hours, which is a slightly more accurate account of pack energy. And of course, we can then use that to calculate a more understandable, perhaps, percentage of state of charge, from 100% as fully charged to 0% as fully depleted. Whatever we calculated and however we accrued that would be a function of how accurately we measured current. And so we originally selected a chip called an INA 225, and right while we were talking about it, they released the new 226 version. This is a bidirectional chip designed specifically to measure current through a shunt. And it can measure voltages down to 2.5 microvolts. Microvolt or a nanovolt. A nanovolt would be, you know, a 1/1000th of a millivolt. Actually, I guess it would be 1,000th of a microvolt. So it's 10 to the 6th smaller than the millivolts we're talking about on this. So it gives us a very, very accurate measure of voltage. It does that with a 16-bit analog to digital converter, and that's a pretty persuasive number of bits. You have to take a output voltage and break it into 65,535 discrete numbers. For example, the Arduino Dewey will do 12-bit, 4,096 discrete numbers, and the regular Arduino will do 8-bit, which is 1,024, or 10-bit, which is 1,024 discrete numbers. So this is 65 times better resolution than the Arduino on the A to D converter. It then presents that as serial data over the I2C bus. And in that translation from analog to digital and presenting it as serial data, it also isolates it. In other words, we have no physical connection between the shunt, which is connected to our high voltage battery pack, and our Arduino, which is receiving the data over a serial port that is isolated from it. That's the reason when we go to all that trouble to put in this INA 226, that I don't want to put a 75 millivolt 0.5 or class 5 shunt. And so we went ahead and spent the money on a shunt that is class 1 or 0.1% accuracy on the resistance. Between those two things, I believe we will have the most accurate Coulomb counter available in any electric vehicle worldwide. There is another device, Sensodyne. We bought some from them. They've been very good to work with. Their product is a little bit complicated, and when you get down to those levels of accuracy, temperature compensation gets to be a big deal. The parts count on the supporting parts got to be kind of high, and it just got to be a little bit much, and so we didn't use that. I believe that would give you the most accurate count, but I can't find an instance of anybody using their chip for automotive applications, which is what it was designed for. It's just a little bit hairy to deal with for a couple of country boys like Paulo and myself in any event. The INA 226 worked out much better. The INA 226 also has inputs to measure your pack voltage. Now, you can't measure several pack voltages. I would like to have been able to measure pack segments, but Ed is working on a device to do that. And so this was supposed to be a quick and dirty and inexpensive version, just an upgrade to the JLD505. We got in over our heads. It's like when you have a clean sheet of paper, it's easy to keep adding things until you go way beyond. One of the things, again, I was the driver on this, was these little Maxim one-wire temperature sensors. They have a system where they make temperature sensors that are each individually serialized, and a chip that will survey a one-wire bus. You hook up as many of these as you want, theoretically up to a couple hundred of them, practically up to a dozen of them, and for our purposes 4 or 5 would normally cover every battery box in your car, to the same wire, and in sort of a serial bus fashion, the master chip on the board polls these, gets their ID numbers, and then is able to query them for temperature intelligently by ID and the current temperature, and keep track of that. We will include one of these probes. I have some that are 10 meters long. I may start including those, let you cut them off where you want, so you have a continuous thing. I've also got quite a few of them that are this about 1 meter type thing. Ends in 3 wires. Maxim has the only 3-wire, 1-wire bus in the world that I know of. Actually, they can these can be powered parasitically from the data line. That's why they call it a 1-wire. You only need 1 wire to hook this up. You do have to hook up the ground somewhere down the line, and but that can be anywhere. But the way we did the board, we actually have the appropriate power for these coming out, and you'll find they're more stable and you get better results if you actually do provide a ground and power. And so you have ground power and your 1-wire serial data bus, and so that lets you do temperature. These are stainless. You can put them in the thing. I would wrap electrical tape around here where it also doesn't conduct, and stick it in a battery box and run it back to the JLD505, and it will be able to report the temperatures on each of your battery boxes, or simply collect them and use the highest or lowest for its own purposes. And so that's the basics. One of the most innovative things we've done with the JLD505 is in our communications ports. This is a Modice cinch enclosure. It's IP67 and totally weatherproof. And Paulo was just wanting to do something with these so bad. And so I said, okay, let's do it. I've never met a connector I liked anyway. I didn't want to learn a new one. However, that said, this has a 18-pin connector that's quite sturdy, and it has a center post pin that holds it in place. And so you put the connector on, and you turn this actual bolt down and tighten it down, and that keeps it totally secure on the device. We ship it with some pins. You have to make your own cable. I'm not sure exactly what you're going to do with all this. So we give you the connector and the bag of pins. I think we're shipping 20 pins for an 18-pin connector. And you can make it do what you want. One of the things that this has cost us is our USB serial port. And there's no place to put one. Here is a bulkhead serial port using the Mini B that I like because it's so sturdy. And this one ends in 4 wires. We actually have our 4 USB pins brought out to the connector as A1, 2, and 3, and B1. No, it's B3 is the USB ground. And so the first EVTV viewer to figure out which of these 4 pins go to which, the 4 wires go to which of these 4 pins, we'll send you a free coffee cup. No, I'm kidding. Actually, I've been working on a book for this the last few days, documentation to show you what all you can do and how to hook it up. And so our main communications is by a USB serial port, and this was one of the issues in staying with the Atmega 328, which is essentially the same chip as used in the Arduino Uno board. And that is that he could use a readily available chipset to do a USB serial port, but it would be isolated. Again, Paulo was big in isolation. I kind of am too, so it works out. We get along pretty good on that. Target of opportunity, actually something we wanted to do from the beginning was, of course, make it CAN capable. And so we have CAN high and CAN low. I think it comes out on, maybe E1 and 2 on the Modice cinch connector. And here, have a peek. And that's kind of on purpose. We're going to have this collect current and voltage and temperature, calculate kilowatt hours, accrued ampere hours, and state of charge, and also carry capacity, which you'll configure. And those will be transmitted on 2 bytes or 2 message IDs, message ID 404 and 505, after the JLD404 and JLD505. Now, you can do any number of things with that. You can retrieve it with any other device for any other purposes you want. Our JevQ I've already modified to work with the EVIC display from Andromeda Interfaces.
As our world grows, it's necessary to invest in sustainable transportation to reduce our impact on the planet and ultimately create economic efficiencies wherever possible. Electric vehicles are becoming the leaders of this efficient, sustainable movement. In electric vehicles, the driver experience is just as important as the batteries that power it. EVs display different information than conventional vehicles, such as the amount of energy stored, expected mileage on a current charge, and distance until empty. Monitoring vehicle efficiency and energy consumption are more critical than ever because of driving range limitations experienced in EVs that are different than your conventional vehicles. This presents new challenges to structure and simplify new driver information for operating EVs. Andromeda Interface's EVIC was designed to collect, interpret, and consolidate data onto one vehicle dashboard to provide a reliable and configurable device to monitor the operation and safety of your electric vehicle. From monitoring your motor controllers to your battery management systems, EVIC is a human-machine interface that seamlessly interprets all the complex data coming from these devices. EVIC presents the driver information in one simple display unit, and we are continuing to build our portfolio of certified interfaces from other EV suppliers. Please review our list of supported EV components on our website. Andromeda Interfaces is striving to enable human-machine technology that helps improve the safety and efficiency of electric vehicles. By doing this in a cost-effective way, we are helping to accelerate the growth of sustainable transportation.
And what it does is gets RPM and battery current and voltage and some other information from the motor inverter and presents it on a digital display. If it detects this 404 or 505 message from the JLD505, it will take current and voltage and state of charge and amp hours and kilowatt hours from the CAN data on this, preferentially over the battery data it gets from the inverter. Why? Number one, the inverter may be off, and the JevQ and the 404, 505 be on. Number two, this will be on when you're charging. And number three, this should be at least 2 orders of magnitude more accurate than that's reported by the inverter. The level of accuracy the inverter needs on battery voltage and battery current to properly invert and drive a motor is pretty minimal. This will be much better. And so CAN bus is the way we will report that. There is another function, because we're measuring current and voltage and temperature and doing CAN bus, we really have everything we need to use this as a controller for a CHAdeMO function, a fast charge function in your car. We're lacking 2 contactors and a relay from being fully there, and we can add those, make a kit with a Yazaki CHAdeMO plug, and this will be able to do the entire CAN transaction with a CHAdeMO charge station to affect fast charge. And so that's the second function of the CAN thing, and it can do all that, transmitting the 404 and 505 messages and doing the CHAdeMO stuff. So it will then show you on your EVIC screen and your JevQ what's going on with the fast charge. Target of opportunity, I'm not there yet, don't have time, but I've always wanted to do these kind of displays for an Apple iPhone, and they now support Bluetooth low energy version 4.0, and that interface is available to you as an application program coder. And so we added a module, the HM13 Bluetooth module, to the JLD505 to be able to do that. And the way I'm going to do that in software is you'll configure it either to do menus and configuration, just like we do out the USB port, or to simulate CAN and transmit CAN messages as ASCII strings out the Bluetooth port. And then you could use those in an Apple program to very efficiently get the data without a lot of querying and response. It would just get a stream of CAN messages with very compressed data about your battery system for display on the Apple iOS device over Bluetooth. So Bluetooth will be able to swing two ways in here. We also have two inputs and two outputs, digital. The two outputs have a MOSFET. MOSFET can switch, I think it's 6.8 amps pulse and 1.6 amps continuously. And it basically is a low side switch. And so when we turn it on, we're tying the pin to ground, vehicle ground. And it can handle up to 1.8 amps that way. So you could use it to turn on a contactor, a relay, an LED, whatever you like. And we have two digital inputs that are optically isolated. Again, they run a little LED and a photo transistor picks that up. A little bit of inversion going on there. I think it's always high unless you apply a 12-volt input, in which case the pin goes low through a pull-up resistor. And so you have two gazintas and two gazatas, and they're very capable. You will be able to configure those for the outputs. For example, we're going to be able to configure for to use as CHAdeMO outputs, to use as temperature outputs, where if a temperature fell below a certain value, you would switch on one of the outputs, or if it went above a value, you would switch it on. The same with voltage, to where if the voltage fell to a certain voltage, you would turn on an output. You could use that to disable your controller or enable a limp mode by cutting your throttle signal to a quarter of its natural level when your state of charge reaches a certain level or your voltage reaches a certain level. And so they'll be configurable for inputs and outputs. And that's pretty much the roundup on the JLD505. The boards will be here next week. We're a long way from having the software done. We haven't really begun it yet. We've tested some things. We have some test software, but we're going to have to generate software for it. And that's going to actually require, because of the new chips, like a new one-wire library to be done, and probably a INA 226 library will have to be revisited, and then we'll have to code up the software to operate this. But I think all that's doable in a month. Of course, I thought I would have these back from China by the second week in January. I'm looking forward to receiving them the third week in March. I'm told they're in the air, finally, at the Chinese New Year to deal with, and some other incompetencies. But that's the trick. And as a product, again, you'll have your enclosure, a connector, some pins, a USB, a temperature probe, a book that probably you can download. I don't know that I'll print it, but it'll be done. And that's what it takes to productize something. You'll have to put that in a box and put a mailing label on it and ship it to people and have it on the website and priced. So there's a lot of little work on this little stuff. Really, the peripheral devices wind up being as much money and as much pain as the main circuit board. The shunt, in this case, probably approaches half the cost of the circuit board or more, but by adopting a Class 1 0.1% shunt, I think we'll have a very accurate and stable current measurement, so you can count coulombs and know the state of charge of your battery pack. So that's our take on a minimalist battery management system that'll accurately count current and voltage and temperature, and have a number of ways and room for growth and change in the future between the three communications ports: USB serial, control area network, CAN, and a Bluetooth version 4.0, which includes the previous versions 3.2 and 1.0 and so forth of Bluetooth. I guess it's 3.1. And so using those channels, we should have a lot of ways into and out of this and be able to do things with it. Another thing that this would do easily is, you know, we sell the TCCH or Elcon chargers that are CAN controlled. I have to make up a little controller to control those. We're probably going to make you buy one of these, and it'll be more expensive, but it'll do more stuff because it's too easy for me to control that charger with this device and not have another device I have to assemble and productize and mostly assemble on the side. So, David, I know what you're talking about. It's a problem, but I hope we can get to something to keep your concept alive. But I do understand that assembling them is probably more work than you want to get into. He's got a little cover here that pops off that has a USB port inside and still has some weather-tight and anemic enclosure. And so I can't wait to get started playing with this with a legacy older style instrument cluster and see what it does. So that's what I've been doing this week. Again, it's not very car and it's not very exciting and it doesn't make great video, but I hope you now have a little better understanding of current shunts and current measurement, and that's a big part of knowing what's going on in your electric vehicle. And again, the mission is to integrate and instrumentize and enable you to use more and better components to make a better car in the future. And I kind of feel like we're getting there, a step at a time. So stay with us. Our little band of ass clowns is growing, that devoted to this, apparently attracted to this concept of reverse engineering things and developing the integration glue for the electric vehicle. Michael Neuweiler has been in and out. He will tell you a little bit more about the Maxim or Dallas one-wire temperature sensor situation. Let's go to Switzerland.
Hi everybody. This week's video is going to be pretty short. I'm going to report on some findings I made with on discoveries I made with temperature sensors, the one-wire temperature sensors, which were mentioned in Jack's previous shows. I found out that it's actually pretty easy to implement some code in Arduino Duo based board and attach them to one input-output channel. The purpose of doing this is I plan to use the temperature sensors to read the temperatures of my battery packs in different locations, and then deciding if any of the battery temperatures is below 5 degrees Celsius, I'd like to stop or not use the charger, but fire up the fire up the battery heating and monitor the battery temperature, and once it's above 5 degrees Celsius I'm going to start the charge cycle. So here we have a Arduino Duo board with some shields on it, some prototyping shields. In the back there's a breadboard to which the temperature monitors are connected, and here you see 6 of these transistors encapsulated in a inox tubing and sealed so they're waterproof. $3 each, so it's really nothing. So they go to the breadboard here. It's a bit of a mess, sorry about that, I didn't have time to clean up. What you see here is the white wires, they're the signal or the data lines where the traffic is going back and forth, and the red one is the plus 5 volt line, and the black is ground. So all the red are interconnected, all the white lines are connected to the same line and also to ground. All you need beside that is here one little pull-up resistor, 4.7K against the 5 volt line. So you pull up 5 volts on the signal line, and then Arduino can pull it down to transfer messages and receive messages. The idea of these temperature sensors, they're called one-wire temperature sensors. Well, you see 3 wires here, that's not exactly one. It would be possible to operate the sensors without the plus 5 volt line, so I could remove the red line and use the data line to provide enough power to operate the chips. But if you want to bridge long distances, it's recommended to use the plus 5 volt, and I have it anyway, so why not use it? Each of these chips has an unique identifier. They're engraved with laser during the manufacturing process. It's a 8-byte address which you can use to query temperature information from the device. Yeah, so I made myself a little application which prints the temperatures to the serial bus USB, or here on the LCD screen. I'm gonna pick one up. So one of the temperatures should go up now. The one in the lower right corner you see is going up. The funny thing is they're quite precise, probably not absolutely, but in relation to each other. If left alone, all the temperature probes show the same temperature, plus minus 0.2 degrees, so fairly good. Yeah, what else do you see here? I bought myself another shield. This is a 16-channel relay board I'm going to use to power the contactors. The JFQ itself and the MOSFETs on the JFQ, they can operate the contactors kilowatt or gigawatt directly, but it's not recommended, and so it is recommended to use another relay in between. So I'm going to use this one, and it will also power other things. So what I did, first things first. So the page I started with is this Arduino info page on Wikispaces. It really describes very well how to proceed, how the sensors work, gives you some example codes, some pictures of the very same temperature probe submerged in water, some more example code, but and here's how you can set it up on a breadboard. It's really well, a good description here. So that's where I started with. Then there's also on the Arduino homepage, there is on the playground, there is some information about one-wire protocols, and the link to a library which you will need. This is here, the one-wire library available for download in this zip file. You just install it and use it. Here on in this shop I bought the sensors, the DS. Oh, sorry, it's a DS18B20. It gives you a 11-bit resolution on the temperature. This means about 0.1 to 2 degrees Celsius resolution. So I put myself together a small program which first discovers the devices. This is the Arduino program. If you start it up, it finds the devices here in this code. It is now object oriented, and you can even set the resolution between 9 and 11 bits. If the temperature probes, they require about 750 milliseconds if you leave them on the default setting of 11-bit. But it's okay, it's a non-blocking call. You can tell them to prepare the data and then query them at a later time. So that's the main body of the application. You set up the LCD and the serial port, find the devices, and then you go to the loop, and what you actually do is call the prepare data to the class, wait a second, and then you iterate over the devices, over the found devices, and print the measured temperatures to LCD and to USB. Down here you can see in the console output, if I clear and reset, how it locates the different devices, prints the address, identifies the family, and then starts outputting the temperatures of all found sensors. Going back here in the temperature device tab, that's the actual class which does all the work, the constructor. You can query the type and get the address, set the resolution. That's all not so important. Here what is important is this is a static method you can call prepare data. It writes to every device on the bus, say please prepare your data, and then here you can retrieve the data. It does some calculation and get the temperature after that from the class, either in degrees Celsius or in Fahrenheit. So that's pretty much it. The code is available in my GitHub. I'll put the address here. Yeah, that's it. Ah, yeah, of course. One thing to mention is that one of I used my makeshift CANDUI board here, which is a kind of self-made CANDUI. Of course, this works very well with the CANDUI board available on EVTV. You just pick one of these digital output pins. Here, the green wire. I picked port 24, and then you go over here. The length of the supported cables, or the supported length of the digital input and output cable is really sufficient for a car. I think it's 50 meters or even 100 meters, so no worries there. So that's it for the moment. My plans are to use this device, this Arduino or this CANDUI board as a separate device alongside with JFQ. Most probably they're going to talk to each other over the CAN bus, so the JFQ can query temperatures or command it to open or close some of these relays on the 16-channel relay board. It's like an extension of the existing JFQ. If the ports are if you need more ports, that's what I probably need to operate pumps, brake lights, and various different 12-volt devices. So the JFQ is going to be the head, which controls everything, and then I have a slave device which prepares the temperatures and controls the relays.
Progress on the Chevy Volt heater, and kind of a related thing, because we have to be able to measure temperature and control this device. but I am much enamored and fascinated with this Ebenspracher liquid heater used on the Chevy Volt. It's actually used on the Chevy Cruze and some other cars that are not even electric cars. But it allows us to take electricity and heat liquid and circulate that. And for any of you doing a conversion of an existing vehicle that has a water-cooled internal combustion engine, the heater, core, and environmentals in the center of your dashboard are basically dependent on two hoses that stick through the firewall, and one of them is a Gazetta and one of them is a Gozada, and what it's looking for is hot water, and that's how it heats your car. We have had various strategies, including a sort of a huge tube with a water heater element in it, an actual element used in water heaters to heat it. Of course, the water heater elements burn out. This device by Ebenspracher works more like a PTC heater. It has little ceramic bricks in it, a bunch of them, bathed in the liquid that flows through it, and those are connected to some IGBTs, which a controller in here applies pack voltage through those IGBTs to those little positive temperature coefficient ceramic bricks. And so it's extremely durable. You're not going to burn it out anything like a water heater element. It's much smaller, and this puppy puts out 6,000 watts. It can be used in systems from about 220 volts, maybe lower you could get away with, up to about 450. And so Michael Nollweiler is also fascinated with this, as are several others. Heading the team is actually Mark Weisheimer, and he has actually had to make some changes. This is going to be a tough one. Not only do we have to reverse engineer the can, but it's not real can. GM has their own system called GM LAN, and that really consists of three networks. One of them is a 500 kbps CAN, regular CAN network. One of them is called LIN, which is a reduced cost type of network for small numbers of very simple devices. But they have a third one called single wire CAN, SW-CAN. And that is a special version of CAN that operates at 33.33 kbps, kilobits per second, and it runs on one wire. The differential is to frame ground, and it requires a completely different chip to even talk. The regular CAN can't do this. And so Mark has had to determine what chip was used inside of here for communications. Get one of those chips, and it is an SW-CAN chip. And splice that on to one of our CAN DUI boards in place of one of the CAN transceivers. This gets even worse. To talk to it, you have to have a wake-up where you drive things to 12 volts from the normal 5 or 6 volt CAN level for a wake-up signal. And so there's some hardware elements to the protocol. So this is supposed to be a simpler and less expensive version of CAN that quickly gets more complicated. It's kind of like having a one-wire network that takes 3 wires. Well, this is a reduced, simpler version of CAN that's more complicated. But I'm pleased to announce that Mark did this week achieve heat by sending some form of data over some form of single wire can to the Eben sprocker, indicating we are going to win, but we're going to have to do some specialized hardware for the controller, and of course some special software. These list at the dealer for $466. We used to pay $750 for a 4 kilowatt heater from MESDEA, which is no longer available. And so here's one done in the millions, or done in the thousands anyway, that I think is much more durable, much smaller, and could fill the same bill. But we have some miles to go before we declare victory on that element. Damien Maguire is continuing to work on the DMOC 645, and let's see what he's got going.
Hello folks, and welcome to part 3 of our inverter build series. So, as we can hopefully see here on the table, we have gotten pretty much everything back together. I've got my current sensor board in, I've got my driver board in, I've got all my bus capacitors back in, screwed down tightly. So what we need to do now is we need to start working on our wiring harness. Now, our inverter control board has got 3 IDC headers. This middle one, the 24-way one, handles I/O. The one on the top handles sensors, so current sensors, voltage, temperatures, that sort of thing. And the one down the bottom handles IGBT drive. So what we're going to be doing now is, now this will probably bore some people to death, but we have our signals from our IGBT drivers here on individual leads, and what we have is we have a common 5 volts and ground rail, and then we have 3 high and 3 low gate drive signals in the purple and black wire here, which we have flagged to tell us what they are, basically. So we have now got this ribbon cable tail that plugs into our IDC connector on our main board. I'm sorry, I heard you have the wrong one, did I? Yeah. So it's the top one does the IGBT driving. So what we now have is we have a bunch of colours here that we need to connect to these wires so that we can actually put some power onto this system. And the first thing that we're going to look for is that our gate driver boards have got power, and then we're going to look at the voltages between the emitter and the gates of each of the transistors, and check that we're getting a negative voltage of somewhere between 10 and 15 volts on the gate, signifying that they're all in the off position. So we're going to get started here, and I'm going to walk you guys through a little bit of what we have done here. Now, I guess the layout of the board and that is such that it was really designed to use just plain ribbon to wire up all of the parts. But I decided to use these individual cores actually going in here to the gate drivers. Perhaps I should have just stuck with the plain ribbon cable, but anyway, it just means that we have one more step in the process, which is basically joining this to this, so it's just a bit of spaghetti. This ribbon here is coming from our current sensor and well general sensor card, and it pretty much plugs in down here, and lets us sense current and voltage and temperature and stuff like that, and I'll be going through that in the next installment. So in the meantime, we're going to concentrate on pretty much getting the tails wired up here. So what I have done is there's been three 5 volts and 3 grounds, so I've commoned these up on the ribbon cable just to give us that little bit of extra area on our cores. So basically, just to run through this, my yellow is one of my VCC lines here, so this means that these ones here will be my grounds. So I've had to kind of just make a bit of a pin map here. So for example, 4 brown is a ground, which we have here. Yellow is VCC, then we have the top and the bottom drives here, then we have a ground here. The next one, black, is a 5 volt, so we want to connect that to our yellow. So black and yellow are 2 of our 5 volt rails. I'm just going to twist those guys together, and we should have one more 5 volt rail down here. So let's see, the purple is a 0 volts, which we have here, and the blue along beside it then is our other VCC line. So I'm going to connect these 3 together. So this gives me my 5 volts and my ground for my IGBTs. These 2 here are just basically spares, we don't use them, so to avoid some confusion I'm just going to snip those guys off and get shut of them. Now, so let's go ahead first of all and put some solder. So we're like wrestling a snake. Let me get myself one of those helping hands things, would be quite helpful. So let's put some solder on here onto these guys, and what that should leave us with then is our power ground and our 6 signals, which indeed it does. So yeah, it can be a bit of a challenge building up this particular design, and I would very much like to get involved with it and see if I could make some improvements. So hopefully that's something I'm going to get to do this year. A lot of pressures and stuff going on around me these days, but I guess it's, if you want something bad enough, you just kind of have to make it happen. So now I'm going to go ahead and put some sleeving. I prefer to use this Hellerman kind of silicone rubber sleeving. It's quite good. Means you don't have to heat the cables or do anything like that. The only problem is you've got to use this lube on it, which can be it's a kind of a silicone lube again, but it does the trick, I suppose. You even complain too much about it. So basically lube the connector and kind of work it on over the wires, and then once they're not liking that, so I guess I'm going to have to try it on the actual ones here. So in this case my pink is my 5 volts and my green is my ground. So you guys are going to get the view of my head again, the old bald spot, and we'll shorten these guys down, rid of the excess. Some Renault battery wiring, very kindly donated. So there's our ground, and strip this guy out and give us our 5 volts. So once I get all this stuff wired up, don't worry, I'm not going to expose you guys to the whole thing. We'll go for a little bit of an ad break now in a minute. Once we get all these signals wired up, we'll be able to put some power to this put some power to this card and hopefully pass our first kind of an electrical test milestone where we'll see that the gates of the transistors are being turned off. So that's kind of the aim of the game today, folks. Fortunately, I just had too much pizza as well, so not exactly the best food to consume when one is kind of thinking, at least for me anyway. So this is my VCC, it's my yellow and my black. Yellow, black, yes, and blue. Okay, so then again, that's kind of hacker food, isn't it? You know, pizza and juice. I guess that doesn't really work for me. Okay, there we go. There's our 5 volts. I'll just pull the sleeving over the connection like that. Tends to work quite well. So let's go for ground, and then I'm going to let you guys take a break, and we'll come back once we have all these guys rigged up. Miracle of video editing that I tend to fail at rather miserably. There we are. Okay, so there's 5 volts. No, not 5 volts. There we go. There we go. So there's 5 volts and ground. So now I've got 6 drive signals and I have 6 gate drivers. So I'm going to make these guys magically connect, and we'll come back when we have that done, and we'll power up this card and see what happens. Okay folks, so we're back. I just rigged up a bench power supply here to supply 12 volts to the inverter board, and we're drawing about 400 milliamps. We're supplying 4.98 volts to our driver boards, which is bang on. We have an activity light on our processor card, which means that the 3.3 volt rail is up and our processor is working. I don't have the USB plugged into it at the minute, but if we did, I'm pretty sure we'd be communicating. So what I'm now going to do is connect up the fluke meter, and we'll go ahead and we'll check all of the voltages on the gates of our IGBTs. With a bit of luck and a prevailing wind, they'll be where they need to be. So let's see what we get. Start off down here with the number 1 transistor. Might be a bit of effort now to get these probes in here because it's kind of tight, but let's see what we get. Okay, there's our first one. Minus 15.1 volts. Nice. Let's go for our second transistor on this package. Minus 15.1 volts. Very good sign. So this transistor here is basically both halves of the brick are basically shut off. Let's try this one. Minus 15.1. And the second side of the brick. Minus 15.2. It's close enough. Let me get rid of this meter here. It's only monitoring that. I was just monitoring the 5 volt rail coming up with this meter here. And finally, our number 3 brick here. Minus 15.1. And finally, minus 15.1. Okay, folks. That is a very good initial electrical test of our inverter. So next phase of the operation, we will be running the test program in the processor card, which basically runs a 1 Hertz complementary square wave into the IGBTs, and we'll check that the driver at the that the gates are indeed reacting to that. And then we'll be looking at actually starting to connect up some of the last things here, like heatsink temperature, DC bus monitoring, and we start spinning some motors. So thank you very much for watching, thank you for supporting me, thank you for all the comments, and we will be back very soon, because this is...
And that is quintessential Damien Maguire. We've had a relationship for several years. I like a little more packaged solution. Damien likes to see what is inside his stuff. And so he does things with a hole saw and some glue and a spanner that I can't go there. But it's always interesting to watch. He has agreed to be our keynote speaker at the Electric Vehicle Conversion Convention, which we hold here in Cape Girardeau every year. This year it's scheduled for the 29th of September, a little bit cooler part of the year, hopefully, than our August event last year. And he will be joining us for that and kicking off the event. And everyone attending AvCon will then get to meet this my Yoda of Ireland, kind of the heart or soul, in my mind, of the DIY electric vehicle movement. And interestingly, he's here in the United States this week on business, and will be arriving in Cape Girardeau, the planning is now, on Wednesday evening next week, and will be with us through Friday. So we will probably make next week's show basically an interview with Damien Maguire, and much chortling and carrying on about electric vehicles. That's the plan at the moment. All things working out with the weather and the travel arrangements. And so we look forward to meeting Damien in person for the first time this next week. And again, he'll be our kind of featured speaker at the Electric Vehicle Conversion Convention in September. And so we're very positive about all that. The DMOC 645, he's kind of hot rodding there. You don't need to drive a car very well. It'll put out, in theory, 118 kilowatts into our Siemens motor, and that's the package we got from Azure Dynamics, and that seems to be working very well. In a lot of ways, it's kind of our top seller. We bought them right and have them priced right. So it's been a popular AC drivetrain. You can't beat an AC induction motor for, it's heavier and less elegant perhaps than our Power Phase 100 from UQM, but it's the strength of a bull and the durability of one. There's just not much to go wrong with them. And so it's one of our favorite packages. And we still have a quantity of DMOC 645s and Siemens motors paired with them, with all the cabling. And you get that and a JevQ, and you have a drivetrain, a very nice OEM quality Siemens drivetrain for an electric vehicle. And so those continue, and you don't have to do all that, but I thought it interesting to run this three-part series of Damien taking it apart and revising it to use a DIY open source controller, that a control board to perhaps glean more power out of the DMOC 645. And so that's what's going to be in his Panzer, Der Panzer, a BMW 840, I think. Kind of the closest thing BMW has to a muscle car. Of course, they have their V12s, but this is the most American-like BMW in some ways. And he's already got the Siemens in there. We'll add the DMAX 645 set of batteries, and he should be coming along pretty well with that project, certainly by EVCON. I doubt he's going to ship it over here, but he'll be appearing. Anyway, that's the show for this week, and I think a good one. We're making progress on many of our products, our specialty electronic products. I'm very enthusiastic about the JLD505, the ability to measure temperature, voltage, and current, and add that onto the CAN bus where we have our legacy instrument driver from David Seabury, and of course our JevQ, which is sort of the master vehicle controller. And so we're developing a little ecoplex here of devices. Ed Clausen has taken a fascination with GSM and GPS and so forth, and I'm kind of hoping he'll boil that down into a board we can use on the CAN bus to get speed and position, and be able to phone our cars and turn on the heater. And so you can kind of see how, as the team grows and the targets are added, that we're going to wind up with a set of devices, multi-controllers, like the OEMs have, but more generic, where you can apply them to any vehicle for your purposes and use their stuff as the major components. And again, as I illustrated last week and talked about at length, one of the main advantages is not just having OEM quality components at a lower price than we've been paying in the past. It's really about building a repairable car to take advantage of the global support infrastructure, the auto parts infrastructure that exists throughout the planet to provide spares and replacements. If you can use those kind of components in your car to whatever degree, that makes it much easier for other people to understand what that is. Sort of tribal knowledge grows, and how to replace it and where to get them, and to be able to get them into the future. Once you have a volt going from 2010 to 2015, you're into 10 or 15 years, 20 years of part support there. These will be available, for that kind of time, just on what they've done so far. And so we continue to pursue that. It's going to be a new direction for us in some ways. Not so much. We've been working at the JevQ for 2 years, but this is where it gets us to, and now we can start adding on other things beyond JevQ to tame the electronics of a modern electric car, and equip you to do the things that are commonly done with OEMs. And that gets us away from forklift motors and chopper controllers and the ad hocism that has engendered up to this point. And there have been a lot of beautiful builds done that way, and that make very excellent electric cars. But I think in the future, this is the path to him in raising the bar and improving that, enabling and empowering you to do better work and prettier cars that are more capable. And in this case, more repairable and tradable. It's less of a mystery if I buy your electric car if you're using common parts that I can get down at Mr. Goodwrench as spares. And so that's kind of where we're going with that. That's the mission, and we're in the throes of it, kind of in the deep part of the trench. I think this, for me personally, is going to be a difficult year. Being involved in that level of, as Mr. Seabury notes, the difficulties of converting it into an assembled product and making those available in quantities is going to have some challenges, and it kind of takes me out of like making electric cars. We'll get a couple people in here and get back into the game of finishing cars as test beds for all this, really. But this is where my work is going to be in the next over the next year, is helping to develop these components and testing them out and getting the software working and some of the bugs worked out, and to where all this plays more like a symphony than a jazz